7.4 arc length and surfaces of revolution. Now, at this point, you know how to find the area of a plane region, how to find the volume of a solid by slicing using disc and Wasker methods. We did not do shells yet, but we will. That's not a required method right now for the course, but we will look at it. We will now learn how to find the length of a curved line and the area of a curved surface in space. So here it says to get out exploration 53 and work through it as a group. We will do that in class as a secondary part of this lesson. But let's, for now, take a curve. Right? And you can see I have drawn several curves. Okay? What happens if I connect points A and B? Is that going to be a good, if I found the length of that, let me see how to find the length. Wouldn't I just make my little right triangle and use Pythagorean Theorem to find that length? Yeah. Well, that's not going to give me a good approximation at all of this curve, of the length of this arc. So what if I put another point in there, and now I said, okay, let's look at two little segments here, and we can, of course, make our right triangles and use our right triangles to find this length and that length. That's going to be a better approximation. What would be an even better approximation? What if I put 3 points on my curve, and now I'm looking at that one and this one and that one, and we can see that, okay, we're getting a lot better approximation of that length of that curve. All right, so now we're getting very confident here, and we're going to add a whole bunch of these, and let's see what happens. All right, there and here and here and here and here. And as you can see, if I were to draw all those little right triangles, you can see that we're getting a lot better approximation of our curve. So how do you think we could actually find a good and accurate number that represents the length of that arc? Well, obviously, what did we have to do? We used our Pythagorean theorem, and we know that if this is C here, that it would be this length. Let's call this x, let's call this y, and we know that x squared plus y squared equals that c squared. And really, we want to think about this as delta x squared, the change in x squared, plus the change in y squared equals, well, let's call this, instead of c, let's call it L, because we are actually trying to approximate L, the length of our arc. Okay, so we'll call this the change in L squared. Now, what made us be able to get closer to this? Well, my change in L, if I go here, my change in L would be the square root of my change in x squared plus my change in y squared, right? And what is going to give us the most approximate value for the length of the arc? Well, that is going to happen as we take the length of our arc, as we take a limit, as delta x goes to 0, in other words, my change in x and my change in y get so small. Notice how they got really small, that I am taking the limit of the sum of adding up all these little arc lengths, the hypotenuses, which are going to represent the arc lengths. And so if I take the limit of, as my change in x and change in y go to 0, and I take the limit, in other words, I push it so that I get an infinite number of these little segments. And these little segments are represented by our Pythagorean theorem. If we get that, if we take our limit as delta x and delta y get so small, there's almost very little change that we can see in them, and I add them all up, then I get my arc length. And that is the foundation for our lesson today. So our formal development of our arc length is defined as the change in L is the square root of delta x squared plus delta y squared. That's the general length of any one chord of the arc. If we take the limit as delta x and delta y both go to 0, the length of the arc is found by increasing the number of chords and decreasing the change in x and change in y. Let's transform this radicand a little bit. Let's factor out of each term a delta x squared. So factoring out a delta x squared would give me 1 and delta y squared over delta x squared. And so I can think about delta y squared over delta x squared as delta y over delta x, the quantity squared. Now we know what delta y over delta x is. As the limit goes to 0, that becomes a derivative. So if we take our sum and we look at this transformed radicand, notice that the delta x can come out. We know that f prime of x equals delta y over delta x as delta x goes to 0. Then our mean value theorem says that the instantaneous rate of change equals the average rate of change. If we have a closed interval a to b, there exists a c on the open interval from a to b, such that f prime at c is a delta y over delta x, or our average rate of change. So now our chord length sum becomes this. Now let's recall that delta x is equal to dx. And so our length of the curve L is the limit of a Riemann sum. Remember, we were adding things up. It was our limit that allowed us to make those segments very small so that we actually got to what looked like the arc. And here is our arc length formula. The length of our arc is from A to B, the square root of 1 plus f prime of x quantity squared dx. That is going to give us the exact length of our curve. So our arc length is found by anti-differentiating on the interval from A to B, the square root of 1 plus f prime of x squared dx. That gives us the exact length of the curve. Now differential form is dl equals the square root of 1 plus f prime of x squared dx. Let's remember, f prime of x is dy dx. dy and dx can be written as separate quantities. So our dl is the square root of 1 plus dy dx, the quantity squared, dx. And we know that this dx outside of the square root was dx squared under the radical. And when we distribute, we get the square root of dx squared plus dy squared. So dl is the square root of delta x quantity squared plus delta y quantity squared. It's easy to remember because it looks like the Pythagorean theorem. You need to know this. Definition of arc length. If y equals f of x is a smooth curve on our interval a to b, then the arc length of f between a and b is L equals the integral from a to b of the square root of 1 plus f prime of x quantity squared dx. If x equals g of y is a smooth curve on the interval c of d, so we are a function of y now instead of a function of x, then the arc length of g between c and d is L equals the integral from c to d of the square root of 1 plus g prime of y squared dy. So let's look at an example. Find the arc length of the graph of y equals x to the 3/2 minus 1 on the interval from 0 to 4. Well, first of all, we need y prime, which is, of course, 3/2 x to the 1/2. So we will substitute in our f prime. we get the integral from 0 to 4 of the square root of 1 plus 9/4 x dx. So we're going to anti-differentiate that. Let's notice our u is 1 plus 9/4 x, so our du is 9/4 dx. So I need a 9/4 here, which means a 4/9 outside. And I am now looking at an integral of the form u to the 1/2 du, which we know anti-differentiates to 2/3 u to the 3/2. Now note that we're going to only use the pattern to get our derivative in the correct form, but we're going to go ahead and anti-differentiate. What can we do to make our work easier? Let's bring that 2/3 out, and we get 8/27. And now substitute our 4 in, minus substitute 0 in. Now to work this out, let us remember the 4's are going to cancel. I get 1 plus 9, which is 10 to the 3/2, minus the 0 leaves me a 1 here. So this would be your exact answer, and this would be your answer with the approximated value. What if I wanted to find the area of a surface of revolution? In other words, we have revolved a function around an axis of rotation, and we now have a curved surface, such as these. You can see here is how we're finding our arc length, but we want to find the area of this surface. What we have is a graph curved in one direction, but rotated in another direction. It forms a doubly curved surface. It cannot be flattened out to find its area, but if you draw chords on the graph and rotate them, you get frustrums of a cone. That means the top part of the cone is chopped off. Here is what a frustrum of a right circular cone is. So if we make those chords small enough, we get frustrums of a cone, which can be flattened out, and using geometry, you can find their areas. In general, the area of a surface of revolution is, the surface area is the integral from a to b of the circumference with respect to L. So we know that our circumference formula is 2 pi r, so the 2 pi can come out here. And r is my radius, which is the distance away from the axis of revolution, dl. Formally, if y equals f of x has a continuous derivative on the interval from a to b, then the area of a surface formed by revolving the graph of f about a horizontal or vertical axis is 2 pi, integral from a to b, r as a function of x times, well, what is our dl? Our dl was the square root of 1 plus f prime of x squared dx. Look at that. So r is our distance between the graph and the axis of revolution. And then here is the formula if we were revolving around a vertical axis of revolution. So if we look at this example in our textbook, example 6, we can see it says to find the area of the surface formed by revolving the graph of f of x equals x cubed on our interval from 0 to 1. Now x cubed would look like this. We just have the part from 0 to 1 sketched, and we revolve that. Remember, we did this in axis of revolution. Kind of looks like a Hershey's Kiss if you think about it. So the distance between the x-axis and the graph of f is r of x. Here is our representative rectangle right here that we are using to revolve. Okay. And we know that f prime is 3x squared. So our surface area formula is s equals 2 pi on the integral from a to b r of x times the square root of 1 plus f prime of x squared dx. Now let's substitute what we know. Our radius is the distance from this axis of revolution up to the curve. Our dl is all of this. Let's do some simplifying math. We can see that here our u is 1 plus 9x to the 4th, so our du would be 36x cubed dx. I have the x cubed dx. I need the 36x cubed dx, so I'm going to multiply and divide by 36. We can see that the outside factor becomes pi over 18. Notice this is of the form u to the 1/2 du form. So u to the 1/2 du form anti-differentiates to 2/3 u to the 3/2. So I'm going to multiply by 2/3 in order to get that 36x cubed dx. What I have here is u to the 3/2 from 0 to 1. Not going to be u because I didn't want to spend time changing my limits. And now we're going to substitute 1 in, minus, substitute 0. And you can't do a lot with that, so our approximation is right here. So the area of this surface of revolution is about 3.563. And there you go. So your TPs for today are numbers 1, 7, and 11. See you next time.